All right, hi everyone. Welcome to our last official lecture and our second last overall. So this week marks the end of the stuff that we wanted to cover in this class. And so you could imagine if we had a final or something, this would be the last thing in scope. Next week we're gonna have Alan's gonna do an hour on FPGAs and digital signal processing, I think.
Yep. I might decide
Yeah.
to focus on one or the other depending on how things are going, but yeah.
Yeah. If you want him to focus on either one of those, just let him know. I'm sure he'd be happy to accommodate. But yeah, this is the last thing that we thought was important to cover for directly for your career in physics. And it's maybe not the most fun thing that we've done. We've done some really fun stuff, but it's probably among the most useful things. And that is making sure you can actually do computational physics effectively. And this is something that's really hard. I'm going to lead in by telling you a personal story about what has happened to me over the past weekend. The thesis of this whole hour is basically going to be lots of scientists do all their science in Jupyter notebooks, and those have their place, but it shouldn't be all of your science all the time. And here's why. So I believe some people in the class are taking Physics 111B right now along with me. And so you'll know there's a lab that we just did on nonlinear dynamics. It's actually, I think they extended the report to B2 tonight, so that may be why some of them aren't here. But anyway, not much context required. It was a computational lab where they gave us basically the differential equations describing some systems. We had to simulate that for a range of parameters and plot some stuff related to how these systems are actually chaotic. Just the idea is it's a thing that needs a big block of computation that is very easily optimized and sped up. They gave us some Python starter code that was, kind of slow because Python. And so I saw an opportunity to, as I do with everything, move over to Julia. And they had a package called dynamicalsystems.jl, which seemed to do exactly what I wanted. You could tell it how to define a dynamical system, and then you would be able to run simulations with it. So I want to go over, first of all, how I even got around to that. So I went to the documentation. I should have had a slide here that had, whoops, sorry. Yeah, there we go. Yeah. So I'm going to just hop over here. You still see this, right? You see the documentation page? Yeah, okay, I'm seeing thumbs up. Nice. So, I go over here, I Google something like dynamical systems in Julia, and I come across this package. And so what I want to cover is kind of what I did to start being able to work with these things. So I get over here, and first of all, I would see this introduction page. Award-winning Julia software library for dynamical systems, nonlinear dynamics. It seems to be all the stuff that this lab's about. So, seems good. And they have instructions here on how I can get started. So pretty directly, I can do those. And down here, there's a description. We don't need to go into the technical details of what it's about, but I could map it pretty easily to the stuff I wanted to be able to do. And I figure, okay, so it seems to be about the things that I want. Let's get into some specifics. So I wanted to find a dynamical system. Let's see if this has something. Yeah. And so they give me the general setup of how it works. It's kind of long, but it's not that hard to follow. And if I scroll down enough, I get an example of how they do it in practice for this specific differential equation they define as du dt equals this function of u that they set over here. And so not only do I have the general structure of how this works, I also have specifics on what the syntax should look like. This thing in bounds in particular was something that it's something specific to memory allocation in Julia, and it sped up my code by a factor of 10 just by adding that little annotation, that little macro. So, it seems really nice. So the key parts here are I could get started on using this really, really easily because this package had good documentation. It had a clear description of what it was supposed to do, how the functionality worked, the and API, which is short for, I'm not sure we've used the abbreviation before, but API is a pretty common abbreviation for application programming interface, which basically means the functions and stuff you interact with directly. So remember the idea of abstraction barriers. We don't need to know all the internals about what's going on to be able to use a code base. I don't need to know how they simulate a trajectory of a dynamical system. I just need to know there is a function called trajectory. And so as an end user of the code, I want to be able to go into their documentation and find that's the function that I want to use. So, that's sort of the first few steps of how I do it. So not only is the purpose of this to say, like, how do you go about reading documentation that's been put together well, or maybe in some cases not put together well, but when you are creating science code, what do you want to be able to do? And really the key feature of this is, imagine if someone were starting from scratch, just learning everything about your library or code base or whatever. What would you want them to know? What are the essential factors in there? And like pretty much every other application in this lab, I could find like a function or something to do it, and like a little code snippet that I could copy and like port to my own purposes. Very little like actually the only actual like code creation I had to do for this was like looping over a range of parameters to be able to like repeat an experiment multiple times for multiple different like initial conditions or parameters. And so the process of finding that was really made really easy. And so here's like a snippet of the code I used. This is just largely from I adapted their Python code to like the format that was in the documentation for this package. And I made my own continuous dynamical system. And I calculated its trajectory over like some number of some amount of time. And so you see the benefits of JIT, 3.7 seconds the first time, but almost all of that was on compilation. And once it's compiled, it's way faster. This is for a thing that took, I don't know, maybe some people who were in the class can remember, but I think the Python took definitely way longer, the order of like half a minute or something. And you had to do this like 1,000 times. So this speed up, I could do that in 30 seconds, whereas in the Python, you might have been waiting like 30 minutes. So, seems like obviously a good thing. So, I might as well, why am I bragging about how well I did in my lab? Which I didn't. I did not do well in that lab. And here's why. It turned out, just beyond finding this package, there was a lot more analysis required of us. If you haven't taken a lab-based class yet, they can be, especially 111B, which is just a few labs, but they're all very big ones. They can be very intensive in terms of they ask for a bunch of things, a bunch of different types of quantities over a bunch of systems. And it's a lot of like discovery on your own, especially this one. You had to find like ranges of parameters that worked, and you need a lot of experimentation. So you had a bunch of plots that we had to make that were very data intensive, that needed like this full set of differential equation solutions, like 1,000 of them over 60,000 steps. I saved the data sets and they were like a few GB each. There were very weird custom computations, some of which I could figure out from the documentation, some of which I did have just have to write from scratch, and a lot of looping over things. Like, so sometimes it's just inevitable that you will have to loop over things, and that's okay. So I figured, this isn't too hard. I'll make a Jupyter notebook. It's not that much analysis. What could go wrong? And here is where I bring in the teaching point. So this slide may be familiar to some of you. It's just straight from my SPS lecture already this semester. A really common computational workflow, and the one that I used here, was to make a massive Jupyter notebook with one operation after another, after another, after another. You do all your setup and solving and everything just in line, in a single thing. And this can have its place. We, Alan and I, have largely lectured off, I think exclusively lectured off some kind of notebook. I used Pluto in the MCMC lecture, but we've used Jupyter for anything alive, I believe.
Yeah.
And it's really good for that because I can just like change something really quickly and like just show all of you what the output is. And so it's great for that. It's great for like quick experimentation. I want to see if this works and not break anything while I'm doing it. But there's problems with using this in more generality. And here's one over here, the consistent state problem. So you might see here, like based on the execution order, you can probably see what I did to get here. I set, initially I set a equals 3, or maybe it was -3, who knows? And then I asked for a squared, 9, but then I went back and reran the cell with a is 4. And I addressed this when I brought up the concept of Pluto, but bringing it back now because it is a serious problem with reproducibility. This a squared is based on a hidden state that is now dead. If I reran everything, I would now get a squared is 16. And there's no way to recover results that I got. And this is a serious problem when you start relying too heavily on just a pure experimental environment for doing something it's not really designed for. Another common problem in a workflow that I see a lot is using them as basically just their own scripts, as you put like a bunch of things in a single cell, like hundreds of lines of code sometimes I've seen in just a single cell, and you run all of that just to make it easy when you do like kernel restart, rerun all. And that just wastes so much computation, especially in Python where you need to start everything from scratch. Uh, in Julia, it's a little better, but if you refresh the kernel, it's still not gonna like save the pre-compilation, so you'll be waiting sometimes even longer. So you see there are some problems with, and then of course there's just, it's a pretty limiting structure. You can't use multiple Jupyter notebooks in connection with one another. I can't do one thing in one of them and another thing in another unless I, specifically say I'm going to like save to an output here and I have to write custom code to save. And then I'm going to pull up the result in this next notebook here and I'll get the result there. But, that's difficult and you have to write, it's like a little bit unintuitive to interface them. And sometimes you do want to do that, but most of the time it's just very restrictive to have to be stuck to only one context at a time. In this case, I fell victim to that. So you'll notice here, this is my directory for the lab. Some good things. I have a directory for data. I have a directory for figures, the things that eventually went into my report over here. It's the text file, it's a PDF. But also I have several different IPython notebooks. This one's HTML for some reason. Because I had this consistent process of, and there's this whole folder as well. I had this consistent process of, I just need to add one more Jupyter notebook and this is going to be perfect. It's not that much work. I can just do it with one more. And, with the benefit of hindsight, I would have just gone and used good structure in the start. So this kind of surprised me because, I care about code structure enough that I like put together and taught a class about it. Like not entirely about it, but like it was one of the more pervasive problems. This lecture was one of the major purposes for me putting together this class. And yet even I fell prey to this problem of, wanting to experiment too much and thinking I could just do it all in one. A bit if it is, I'm going to have slightly more relaxed standards when this isn't critical software. I'm putting together these analysis notebooks just purely to generate my report, and no one else is really going to use it after that. But I still ran into problems because I had these like really long notebooks with really intensive processes, and I had no idea where to find anything. This isn't even the worst I've done. This is admittedly a directory from when I was a freshman. This is my first research project ever, and I had basically never been told Jupyter notebooks might not be the thing you always want to use. I sort of discovered that when I was doing research my like sophomore summer, and I ran into problems with dependencies, and I started reading up on like how you do good code structure, and I started like teaching myself a bit of that. But back then, I didn't know any better. So I have all these notebooks with like least squares reconstruction, least squares V2, linearity test, mode basis optimization, and mode basis separately. A bunch of these just called wavefront slopes. So if I want to find where I did a thing, I have to do a bunch of like manual trawling with these things. There's some .py files, there's some IPy and Bs. There's testcec and testcec2 with nothing to say what distinguishes them and which one I should be using. It's just, I have an image in here. This is not how you want to do your science. I'm just fully like roasting myself here because I think it's destructive to see like, you can go into this with the best of intentions towards structure and it just like ends up a mess. And it's not like something you should blame yourself for, but it's just a reminder that you have to stay aware of how easily this can happen. This was also like after I went back after doing this project and cleaned up a bunch of the files I wouldn't need before. This was way worse when I was doing it originally. So you see this as like a real problem. In reality, you're going to make a bunch of changes to your code as you go through the project and your project needs change, or you try to do something else or something like that. And you're never going to be able to find what you need if you do it in this ad hoc style that's like easy to do when you're doing it, but really hard to maintain. Where do I find a certain result that I was just showing last week? If something breaks, how would I even know it? And where would I go to fix it? So it's a serious problem that actually affects computational workflows. And it's really not acknowledged enough because, most classes out, like in physics and astronomy, just use like the ones that are computational will just use Jupyter notebooks fully. I'm fairly sure 77 mostly or exclusively uses them. Someone who's taken 77 can correct me on that. Uh, but and that's not necessarily a bad thing. For a simple example is like our like first three homeworks. It's arguably a more intuitive way to present the homeworks to say I have a single simple thing and I want to just present that entirety in line for you to see exactly how it's done. And it's exactly very clear what I'm doing, what I'm asking you to do. And I can write text around it and it just looks nice. But it's not something you should really rely on for core functionality. So how should it work? What I found out while I was doing this lab is there's this Julia package called Dr. Watson for, support during your investigations. uh, that just makes a suggested project structure for science. You don't have to adhere to this exactly. You don't have to use the package, but something like this is pretty common to science, like something like this structure. At the top, you've got a project directory. All your core functionality goes in SRC. You have maybe some scripts that generate results. You've got like some other things to do with the science itself, like research stuff in progress, papers that come out of it, papers you're referencing. You have something to save plots to. You have something for raw data, and you'll notice that I did some of this. Even in my lab, I had a data folder, and in like more serious projects, I do have a notebooks folder. And there's also some other stuff there that's just like for more general CS projects, not necessarily science specific. Like you've probably seen if you've looked at GitHubs at all after I lecture on them, they all have a README with just like the text that shows up on their GitHub page. And they also have a git ignore, which is just like when you have like system files that you don't necessarily want to make a part of your directory, you can exclude them by putting that in. Like if you're a Mac user, you would have sometimes seen files labeled like .ds_store, which are just like something local to Macs that you didn't want to save. But I've committed and pushed a bunch of them because I didn't know about git ignore before. So this is the kind of like good structure that you really want to strive for in science. Like not necessarily all of these points, but very clear separation between things. So a bit more on that is you have a bunch of places where your code could go. And generally, like they recommend, and I agree with, if you have core functionality, anything that doesn't generate an output, but there's just like functions and classes and stuff that's used, that should go in your source folder or SRC. Anything that generates an output, like run a simulation, save a data set, or something like that, that should go in scripts. And if you're just experimenting or playing around with something, that should go in notebooks. So the way your life cycle would work is something like, you get an idea, you write it in a notebook, you're convinced that it works once you've done your like little hacky experimentation phase, and then you move it to a source file and you like think about how that should work. And that's a little bit annoying, but it will pay dividends. And if I'd done it, I would have a better lab report than I actually ended up turning in. Okay, as a programmer, now we're going to move into a phase about like actually writing good code. And so this disclaimer up front, no matter where you are in programming, you're going to end up Googling for stuff constantly. Everyone does it. It's completely okay. You're not a worse programmer for having to look up like how to do subplots in Matplotlib. Literally everyone does that. You can have years and years of experience with it and you're still looking things up, and that's totally fine. You're not expected to have 100% of the things off the top of your head, but what's more important is you know where to find it and you're confident that you could find it. But don't worry if you are Googling a lot. Okay, so with that, let's talk about debugging. Suppose you know something's wrong with your code, and how you know is, you'll have tests or something, or you'll see an anomalous result. How do you find and fix it? The most common method I'd say people use, and again, I'm not immune to this, is print debugging, which is just like at every you go through in your head and you do some sanity checks. You're like, okay, if this is this result, then that must have been caused by that, or something like, okay, I want to see if this first step works. I'm going to print out the output and see if it's what I expect. And that can be effective, but not nearly as effective as the optimal strategy. Again, we all do it, but it's not the best way to do it. And that's why most languages, including Python, including Julia, including, I think, basically anything else with like decent support of any kind, will have a debugger out there somewhere. And a debugger is basically a tool that will do this process of that you're doing in your head for you. The process of, if I have 10 steps in my computation, I'm going to do step 1, check if that's right. Step 2, check if that's right, and so on. It'll run through that for you. So imagine like a sequence of instructions that a compiler or interpreter gets. And suppose that instead of running them all at once, when I do like, I don't know, when I run like a Python file or include a Julia file, that it stops after each one. And that interface would look something like this. This is a Java debugger. And so over here, you've got the code that you're testing. This is a very simple example just for like demonstration purposes. Over here, you'll have access to like what the variables in scope are at any given time. So right now, I've just defined A is 5, B is 10, but I haven't run this line yet of return A plus B, because then the next step would be compute A plus B, say it's 15, and then return 15. And up here, you have tools to basically step back and forth in time. So in particular, there is these 4 features. They might have different names in different debuggers, but the idea is generally the same. One is breakpoints, which are points at which you tell the debugger to stop execution until you tell it to do something else, until you tell it keep going. Like, I'm okay with what we're at this breakpoint versus I'm not okay with this, let's just end it right now. Like just a point where you want to pause and look at everything, look at all the variables in scope and what's about to happen. Step into is if you've got a function call coming up, you can go into the function and do this debugging process line by line within the function. And you can do that recursively as well. If function calls another function, you can step into that as well. If you're confident that that function works, though, you don't necessarily want to step through everything that goes on inside. And this can get especially useful when you get like really big code bases and you like trust smaller parts and you're building on them. So in that case, you might want to just step over them. Just like, I'm going to just skip to the end of this function, get the output. I trust that output's right. Let's move on. And sometimes, you'll be in the middle of a function. And you're like, okay, well, I found whatever I need to find in this function, or it turns out I actually do trust this. So you can step out of a function call and go back to whatever scope you were in before that. So visually, that looks like this. I forget, it's been a while since I used these. Yeah, looks like that one step over, this one step in, this one step out. So debuggers usually have a decently intuitive visual interface. In Julia, they're a command line tool, but I'm pretty sure there are also nice graphical based debuggers. I haven't used them enough to really say. Okay. Next up is assorts. In Python and Julia, for sure, and maybe some other languages, you can assort statements, which basically means if they're false, you throw an error. A really common thing that I use this for a lot is to check if the shape of a matrix is correct. If I'm filling up a matrix with some like features that have like importance for science or whatever, and I'm doing it like column by column or row by row, I might want to check at the end that I have a matrix of the right dimensions. And so then what I can do is just add in like assort the shape of the matrix is this shape that I predefined. Like if I have filled in like 3 rows, 5 columns, I might want to assort np.shape m equals 3, 5, something like that. In Python, I find it pretty useful to use this as a replacement for type checks. So we've covered before how Python is dynamically typed, and that means it's way too permissive. It's way more permissive than it should be and lets things run when maybe they shouldn't. And so in Julia, I might say require that an input to a factorial function is an int64, but I can't ensure that in Python. What I can do instead is just manually put in an assort saying assort is instance and int. Assort ends an integer, and you see, put in an integer, it passes fine. But I put in a float, throws an assertion error, it stops execution. So these are really useful, and working with them will help you basically do print debugging but smarter. So you don't have to like manually look through everything that gets printed whenever you print. And you can be more sure once you've passed the assorts that everything you've got is correct. Okay, tests. We want lots of them. It's really, really easy to break something and not know how it got broken. Coding is just like, at a certain scale, it just becomes way too complicated to hold all the facts and information about how everything works in your head. And so you want your code again to work for you and tell you when something's gone wrong. So we talked about continuous integration with Travis CI a few lectures back when we were talking about Git and GitHub. And so you want that to be like checking something useful. Whenever I run the build task from Travis, I want that to be like a guarantee that everything important that needs to run is running. Did you have something?
Oh, I was just gonna say, like, when you work for like a big place, if you're doing that, one of the really helpful things is they have a whole CI chain set up. So every time you push a commit, it'll test all your code and make sure that you don't have any like you didn't add any bugs that make stuff not work.
Yeah,
Um,
it is. Yeah,
yeah, and at more software places, like you sometimes even get to the point where you're writing code and you push a change, and then there's automated tests that happen on that code, and those automated tests happen, and then the code automatically gets pushed into production. And that's yeah, that's continuous deployment. And so if you have really good tests, you can do fun things like that. Yeah.
yeah. I don't think many open source projects really have continuous deployment. Many don't really even have continuous integration. Like the better maintained open source ones do. I've seen that more in recent times, but a lot don't. So, if you're joining a project, then like actually this is a really good thing to do to like volunteer to do when you're starting out. If you're joining a project that's basically like maintain this big open source thing or like do something with this big open source thing, and your task is basically like learn the code base, which is very common, then a good thing to do might be go through and like write tests for the things you want to learn. You check your understanding by doing that, you add value to the project, and you can set up continuous integration, and you get guarantees that it will build and will run correctly on a wide variety of machines. So how you write tests should be informed by like your understanding of the physics or whatever else is going on. Uh, so the two main things I'd suggest are either you're like rerunning some calculation that it's possible to do by hand, or you're using some like slower, easier method with the same thing. For example, if you're like writing a fast Fourier transform by hand, like you write like a recursive definition of, you break it down into odds and evens Fourier transform those and combine them. Um, you might want to check against like the built-in Fourier transform and see if that's the exact same result. Or like even more simply, if you're writing the first fast Fourier transform for the first time, you might want to run the naive like discrete Fourier transform by like summing over exponentials and check that that's the same result. Sometimes you're going to have random functions, in which case it's really useful to fix a seed, which can be done in NumPy by like np.random.seed and some number in there. A seed's basically like a start point for generating random numbers, meaning if you have a fixed seed, it will always generate the same random numbers in that function call or in anything else you do later. So that's a way you can like fix random behavior and make sure you get consistent results even when it's not necessarily a consistent process. Alan, can you check general on the Discord? I think Kyle is trying to get in, but I don't know that I set up a password ever. Yeah. Okay. We talked a bit ago. Oh, I think here he is. Oh yeah, we're good. Cool. Yeah. We talked a bit ago about code coverage. And how you could have like 74% coverage, meaning 74% of the lines of code in your project are covered by a test, and this number you want to get as high as possible. And so that's a really good indicator of how well you're doing at testing everything. So if everything's well tested, then as soon as you introduce a bug by like doing something in code you wouldn't expect, which will happen, it happens all the time when you're implementing something, it's just such a big process, that you'll be able to find that really fast and hopefully fix it really fast. So really in all these cases, you're having your code do a lot of the work for you. You're avoiding a whole lot of manual labor by using good structure and by using like tools that are made exactly for this purpose. Okay, so those are some of the good coding practices that I think will help your efficiency. Others are commenting and writing doc strings. So Python and Julia both have they have two kinds of text in code, and you should be using both of them. You've probably seen comments quite a bit. there are, the things with the like hashtag line of text in like green or something, which are one or a few lines explaining like something small that's happening. Like whenever we put like your code here in the homeworks, that's just a comment. And a doc string is a longer description that's like at the top of a function header or a class header that like describes like what it is, if it's a function, what it takes and what it returns, if it's a class, what it's got as attributes and what it can do, what methods it has. And oops, sorry. If you call help on something in Python or a question mark object in Julia, you can get its doc string. So just give me a minute and wait, let me unshare real quick and close that. Yeah, so you can get its doc string. And where am I? There. So here's a couple of fun examples of that. I'm really just putting myself out there to be roasted here. Okay, so this is a Julia example. In Julia, the doc strings are in triple quotes above the function call. So like this. So here is like a description of what it does, the arguments it takes in. So in this case, it's like an array with length 3n, and like everything else you need to specify about the system. And it returns this, it returns this thing, the array of velocities and accelerations with a length 6n. So you reading that, when you call like question mark inverse square diffeq, you'll know exactly what to expect. And you'll see I've used asserts over here to like check some things about the input, check there's at least two bodies to interact with. And so this is actually for the homework that we've technically got due tomorrow night, but really like we don't have any homeworks after this, so you can turn it in just anytime before the end of the semester. And here's how you might use comments. You might write like, I want to make a loop over all the bodies. And of course I won't give you the exact syntax because that's giving away too much of what's on the homework, but you loop over all the bodies, you loop over all the ones that first body is interacting with, you do something to compute the acceleration component I. And so, you describe what you're doing as you do it. And I've also got this like little comment here saying dispatch on units is a little strange, justifying why I need to have like an if then for something that I would think multiple dispatch should handle. So that's the kind of thing you can use comments for, like explanatory for like minor things that are happening step by step, and for like clarifications on why you chose what you chose. Okay, here is a Python example that is not as good because I did it like 2 years ago. I haven't had a lot of audience participation in this one because it's pretty much just this is how things are done and like a straight like lecture at you. So here's your chance. There are several issues in this, several things I do not like about this code, and we'll be going back to change later when I come back to this project. Just scan over it real quick, point out anyone. A hint might be to check the signature of the function. Way up here.
And then look at the parameters that the documentation says it has.
Mm-hmm. No guesses? Come on, this is your opportunity to roast me. Oh, yeah.
Is it the truth is an ND array? Because I feel like that should imply it's a Boolean.
Yeah, that's maybe bad naming. That is one thing. Yeah, I didn't even think of that. I'm like simulating like some sort of imperfect observation, and so this is like the true values underlying it all. That could be a bit more of a descriptive name. That's a good one. Anything else? There's one really big one that I like do not like about this.
Is it the noise equals noise?
No, that's fine. That just says like I define noise elsewhere in here, and that local parameter has the same definition as the global one.
Is it because delay doesn't exist?
It is because delays doesn't exist. Yeah, so at some point I changed this function to not use delays as a parameter in here. It looks like I changed it to like self.delay over here. But I didn't, and I updated the signature, but I did not update my doc string to go with it. So there's a few other things that I don't necessarily love, like the fact that like literally all of this could be like 2 lines of NumPy if I'd known better at the time. But that's the really big one. And you'll see even here, I've like put comments describing like why things are what they are. The controller is expecting open loop, and I use that one. It's expecting closed loop, and I use that one. That kind of thing. And like over here, what shifts is. So, you know, some things I would do over, but this is the general idea. I didn't have to look very far for like places where I wasn't the best about my own documentation. I want to emphasize really, when you're in the thick of it, like doing science, it is really easy to forget about these good practices. And it might be frustrating a bit to slow down and think about future usability for yourself and for others, because, you know, I wrote this code 2 years ago and I come back to it and I have no idea what's going on. And it's only because I put in the comments that I did that I'm going to be able to relearn it. So, you know, it's a bit of a hassle. It's a bit of a time investment, but absolutely 100% worth it. Okay. A really common principle in computer science is not to repeat yourself. You can, if you're working in a Jupyter notebook and you're like, just like, I'm going to need to do this exactly twice. You can just copy a cell down. I did that in this lab. But anything else, and definitely when you're writing stuff in a source file, you should never repeat yourself, because you don't want to introduce any more opportunities for errors than you've already got. Repeating code gives you more chances to get things wrong, and it hurts the idea of modularity if I can just switch in and out parts as I need to, because, you know, I would need to track down and switch out like many parts just to be sure. Like if I have to make a change like 5 times to like change a number 3 to 4, you should just have a variable for it and just set it to 3 up front and only change it to 4 one time. So, you know, you can combine related functionality through like this kind of abstraction, through like higher order functions, through like functions calling more general ones. So in this case, this is another one from my sparse transforms project, where I want to take like a fast Walsh-Hadamard transform or something with this function sprite. Walsh-Hadamard is like Fourier transform on a Boolean basis, doesn't really matter. But I could also just do this as a Fourier transform, in which case all I would have to do is write FFT over here instead of FWHT. It's just the function that gets called within transform. I don't want to have to write the like 150 lines of code that this is twice, when I could just pass in a function to another function and get away with only writing it once. Also, this one I found kind of fun. Don't repeat yourself is pretty commonly abbreviated to dry, and people apparently refer to the opposite of dry as wet for write every time, or any of these others. That was kind of fun. Okay. So I thought I'd end my part of this by describing my life cycle for a computational science project when I'm doing it like seriously for my own research and stuff like that. I try to make prototypes in a Jupyter notebook or a Pluto notebook, as the case might be. Once I've got something working, I will move it to a source file, a .py or .jl. I'll make a Git repository and a GitHub and commit to it really frequently. Once I've got something in the source files, I'll write tests for it to make sure I don't break it later on. Whenever I've got like a new feature I want to try out, I'll write that as a notebook. Another point I should add over here is whenever I have something to generate a data set or like simulate something, write that as a script separately from your source. Like your source should not like produce anything. It should just be functions that your scripts and notebooks can use. Also, this is a really like underappreciated trick. In Python, when you're working with a package and importing stuff from it, like you've got like my science package. If you want to refresh the source, if you want to like make changes in the source and have them like continually update in your Jupyter notebook, one way is to like refresh the kernel every time you make a change, but that's really annoying and that loses you a lot of time. So instead, you should add these in. And the Julia package revise, which I had to install as part of homework 4, does the same thing as this, pretty much. So this is really useful. This is called like IPython line magic. That's like a technical term. Okay.
I actually didn't know this one. I'm going to use this in the future.
This is very useful. I don't know what autoreload 1 is, but you can Google that, I'm sure. Right. And now I'm going to hand over to Alad for a demonstration of doc tests, the last thing that we're talking about today.
Yeah, I'm actually going to talk a little bit about a little bit more than doc tests because I got the second part of my demo running.
Nice.
Okay, so this is an example directory structure for a Python project. So this is just like it's the tree. Oh wait, this is an example directory structure for a Python project. So we've got this big docs folder with a bunch of auto-generated documentation, which I'll show you in a minute. And then we have, so this is the bootblop project. Inside that, there's a bootblop folder, which is a bootblop, the bootblop module. And then there's a README file and a setup file. So let's just take a look at one of these files. Bat bootblop slash boop.py. So if you look at this file, you'll notice that so we have this doc string, right? Inside this doc string are lines that look like they were entered into the Python interpreter. And these lines serve two purposes. One, when you generate documentation from this, which I'll show you the generated documentation in a second, these lines give you an example of how to use the project. But the second purpose they serve is these tell a tool called the Python's doc test module, which is built into the Python. It'll search a doc string for a function and run like the lines where you have the things that look like it was entered into an interpreter, and it will check to make sure the output matches what's here. So that's what this line down here does. So it says, if I run this file as a Python script, so I'm not importing it as a library, do the following thing. Import the doc test library, which is included in Python, and run doctest.testmod on this module. So let's just do that. So I'm going to run the Python file, bootblop slash boop.py, and I'm going to run it in verbose mode. And you'll see it runs the tests that I had in the doc strings. So these doc strings, although they're kind of weird because they're integrated into a comment, and not a lot of languages do that, they're very easy to write. A lot of languages it's annoyingly hard to write tests. Python, it's very easy to do it with doc tests. So you'll see it'll run boopinator 5, and it'll say, I expect this, and it was okay. I got the right answer, right? And it'll keep doing that. And then it ran this test. So it'll do, it runs, in a list comprehension, it runs this single boop 3 times, and it expects, what I put in the doc test is it expects boop out 3 times. What actually got returned is, so it expected this, right? And the test failed. And the test actually failed because I wrote my test wrong. Because if you've ever used Python, we can see that single boop does not return anything. So if you run it 3 times like that, you'll have a list with 3 nuns in it. So if you just care about the tests that did not fail, then you can get rid of the -v argument when you run your Python script on the file, and it'll just show the failed one. And then it's really easy to fix that. You just, you add into your test, in this case, because the test is wrong. If your code was wrong, then you get the same thing. And you add in what the actually expected result should be. And now if I run that, there's no output because they all passed. And if I do -v, I can see they all passed, right? So the other thing that these doc strings let you do is they let you auto-generate documentation that looks kind of pretty. So I did this just a couple seconds ago. I generated documentation using Sphinx and the default theme. And if I look at I can look at the index, and I can see there's, or that's the module index, probably more clear. I can see there's 2 modules. There's under bootblop, there's bootblop.blop and bootblop.boop. And you can see it contains, those doc strings, right? Now I get this nicely formatted documentation for both of these modules that with the program and then the description of what it does and the the test that I used as an example of how to use it, which is really nice. And this is using Sphinx. I'm not going to go over exactly how to generate this documentation because it takes a hot minute and it's kind of confusing, but there are a lot of really good tutorials online. So I recommend you look that up, and I will post a link to one of those in general. And the other thing that adding nice, as ETT mentioned, the other thing that adding nice doc strings does, and I just wanted to do a live demo of it just so you can see what's going on, is it lets you query for help when you're in the interpreter or in a Jupyter notebook. So if I import booplop, then I can do help booplop, right? And it'll say, okay, booplop has two has two like things inside it, blop, blop, and boop, and I can get help for those. And I'll say, oh, there we go. And it can say, okay, now this module inside booplop has two functions in it, and it'll tell me the documentation for both of those. And this is really handy if you just want to get help for something. So that's just something I wanted to demo really quickly. Sorry, I went a bit fast because I misjudged how much time we have. I see we have one question in the chat. Yeah.
Oh no, that's just me adding on where doc strings go in Python versus Julia. I
Yeah.
think you're good on time, but are there any questions on any of this?
Yeah.
Right.
Are there questions? I'll just show off. I'll just show off Sphinx to convince you that it's nice to use. So Sphinx generates docs in the docs folder. And if you update your program and you want to regenerate the docs, it's really easy. You just go to cd docs, and then you do make HTML to make HTML docs. If I want to make PDF docs, I can do make PDF. Or no, that is not an option. I can make latex PDF, LaTeX PDF. It'll build it and oh, apparently I need to install LaTeX properly on this computer. Apparently I don't have it. But you get the idea.
You could do that.
There's what?
If you did have LaTeX, you could do that.
If I do
Try
have
text.
LaTeX installed, running that command would have made it did actually make a tech file, and then it would have rendered it as a PDF.
Wait, try make text. That one should be easy to like show off as well.
Text, yes.
Yeah.
Where did it put it? Yeah, so if we go to text, it's just going to be a simple plain text formatted file. So bat indexes are going to give us the index, and there's not much in the page, but it's just like simple restructured test. And then bat, you can see it gives you like I think this is restructured test, not markdown, but it gives you like basic documentation. And it's just a really nice tool. Setting it up takes a couple minutes, but there are really great tutorials online. And if you go to any Python project, it probably has its documentation generated with Sphinx. So like requests is a really common library that people use a lot. So if we go to requests, and you scroll all the way down to the bottom, you can see it uses the same theme we do. And it probably says on here somewhere that it was generated with Sphinx. It doesn't say it on here, but I guarantee it was generated with Sphinx because I used their configuration file as an example for my code, which is why it looks exactly the same.
There are no more guides. You are now guideless. Okay. So there are 1 minute remaining. I'd just like to remind everyone that it would probably be a good idea to work on projects now. Like we didn't really want to take up your time like during Dead Week and Finals week with this. Like anything you can turn in by like the start of Dead Week or whenever you're comfortable working on it is good, and working on these things sooner is better, which is advice I will give you and then proceed to completely ignore in my own projects that I have due for classes. Yeah, but if you need any help with that or with anything we talked about today, please don't hesitate to reach out as always. All right, thanks for joining.